Welcome to Ozark Ecology. If you've spent any time in the Ozarks, hiking a hollow in Arkansas, fishing a spring creek in Missouri, or just driving those winding two-lane roads through the hills, you already know there's something different about this place, something that's hard to name at first. The hills feel old. The streams feel cold and clear in a way that surprises you. The forest has a layered, dense quality that seems to hold things in. And that feeling is real. As you progress through our Ozark Ecology course, you're going to understand why the Ozarks feel the way they do. You're going to learn to read this landscape like a book. But before we can understand what's alive in the Ozarks today, the wildflowers, the frogs, the warblers, the cold spring fish, we have to understand the land itself, because in ecology, everything starts with the ground beneath your feet. So in this first lecture, we're going to ask a fundamental question. How did the Ozarks come to be? And what does the physical landscape mean for the life that calls it home? Let's start with geography. The term Ozarks gets used loosely, but ecologically and geologically, it refers to the Ozark Plateau, an uplifted dome of ancient rock spanning roughly 47,000 square miles, centered on southern Missouri and northern Arkansas, with extensions into northeastern Oklahoma and southeastern Kansas. Now, this is not a mountain range in the traditional sense. The Ozarks weren't pushed up from below by colliding tectonic plates like the Rockies or the Appalachians. Instead, the plateau was formed by the slow uplift and erosion of an ancient dome. Imagine a blister rising on the surface of the continent, and then time, water, and weather cutting it into ridges, valleys, and the hollows we see today. That process took hundreds of millions of years, and it left behind something remarkable. A landscape of high, rolling terrain dissected by hundreds of streams and rivers, underlain by some of the oldest exposed rock in the interior United States. Now, the Ozarks are often called a highland rather than a true mountain range. The highest point in the Boston Mountains of Arkansas sits at just under 2,600 feet, and that might not sound dramatic compared to the peaks out west, but in the context of the surrounding lowlands, the Mississippi alluvial plain to the east and the Arkansas River Valley to the south, the plateau rises sharply and distinctly. And elevation matters enormously in ecology. Even modest differences in elevation mean differences in temperature, moisture, wind exposure, and soil type. Those differences, multiplied across thousands of years, produce different communities of plants and animals, which is part of why the Ozarks punch far above their size when it comes to biodiversity. Within the Ozarks, ecologists and geographers recognize several distinct subregions, and it's worth knowing the broad strokes of each. There's the Salem Plateau, that's the largest section, the core of the Ozarks, centered on south-central Missouri. It's characterized by deeply dissected terrain, clear spring-fed streams, and extensive upland oak and hickory forest. This is classic Ozark country. the landscape people picture when they hear the name. To the north and west, the Springfield Plateau rises slightly higher and sits on different bedrock, more chert and limestone. It's slightly drier and historically had extensive glades and open savannas. In the far southeast of Missouri, the St. Francis Mountains represent the oldest exposed rock in the region, Precambrian granite and rhyolite that's been weathering since before complex animal life existed on Earth. Ecologically, these rocky, acidic soils support plant communities you won't find anywhere else in the Ozarks. And then there are the Boston Mountains of Arkansas, the highest and most rugged portion of the plateau, with deep forested hollows, narrow ridge tops, and a topography that can feel almost Appalachian in its drama. Some of the most intact old-growth fragments and richest biodiversity in the entire region are found here. All of these subregions share a common geological story, even as they differ in their details. And to understand that story, we have to go back, a very long way back. The rock beneath the Ozarks holds a record of almost unimaginable time, and geology, more than almost anything else, explains the ecology of this place: the soils, the water, the plants, and ultimately the animals. So let's walk through the Ozark geological story in broad strokes. About 1.5 billion years ago, well before complex animal life, the core of what is now the St. Francis Mountains was an island of volcanic rock rising above a shallow sea. Granite and rhyolite cooled and hardened here, and they've been sitting in roughly the same place ever since. These rocks are geologically ancient beyond comprehension. For context, the dinosaurs went extinct about 66 million years ago. The St. Francis igneous rocks are more than 20 times older. The rest of the Ozarks has a different and somewhat more recent origin story. Through the Paleozoic era, roughly 550 to 250 million years ago, the region that would become the Ozarks sat beneath a series of warm, shallow tropical seas. Picture the Bahamas, but covering the middle of North America. Those seas were rich with marine life, corals, crinoids, brachiopods, mollusks. When those organisms died, their calcium-rich shells and skeletons accumulated on the seafloor over millions of years. Compressed and cemented, they became limestone and dolomite, the dominant bedrock of most of the Ozarks. This is one of my favorite things to show students who visit the Ozarks the first time. Walk up to almost any exposed limestone cliff face in the region and look closely. You'll see fossils, ancient sea creatures locked in the rock. The Ozarks were a tropical seafloor, and that seafloor is now a highland forest full of deer and warblers. That's a remarkable transformation. Now mixed into those limestones and dolomites is a material called chert, a hard, fine-grained silica rock that forms nodules and layers within the softer carbonate rock. You know chert. You've seen it. It's that white or gray flint-like rock you find scattered in fields, on creek banks, throughout the Ozarks. Chert was used by the indigenous peoples for thousands of years to make arrowheads and scrapers, and it weathers out of hillsides as the softer limestone around it dissolves away. Here's where it gets really interesting ecologically. Limestone is a calcium-rich rock, and it dissolves in slightly acidic water. rainwater, which picks up carbon dioxide as it falls through the atmosphere and becomes weakly carbonic. Over millions of years, this dissolving process carves a very specific type of landscape called karst. Karst is the defining geological character of the Ozarks, and it has profound consequences for ecology. In a karst landscape, water doesn't just flow over the surface in streams. It seeps into the ground through cracks and joints in the limestone, dissolving the rock as it goes, slowly carving out underground channels, caverns, and caves. The Ozarks have thousands of caves. Missouri alone has over 6,000 recorded caves, more than almost any other state. Underground, that water travels through a network of passages until it reemerges at the surface in springs. And Ozark springs are extraordinary. Missouri and Arkansas are home to many of the largest springs in the entire United States. Big Spring in Missouri, for example, averages over 200 million gallons of water a day. Greer Spring, Round Spring, Mammoth Spring in Arkansas, these are places where the underground world pours out into the open, cold and clear and loaded with dissolved minerals. That cold, mineral-rich, highly oxygenated spring water creates a unique ecological niche. It stays cold year-round, in the 50s Fahrenheit even in summer. And that coldness supports communities of fish, invertebrates, crayfish, and plant life that you won't find in warmer streams. Smallmouth bass, native darters, Ozark cavefish, watercress. These are organisms adapted to cold, clear, spring-fed conditions, and they exist here because of karst, because of geology. And above ground, karst creates another feature, sinkholes. When underground caverns collapse, or when surface rock simply dissolves away, you get sinkholes, bowl-shaped depressions in the landscape. In some parts of the Ozarks, particularly the Salem Plateau, the landscape is almost entirely shaped by sinkholes. Water that falls as rain simply disappears underground, rather than flowing in surface streams. These are sometimes called dry hollows, valleys with no stream, because all the drainage is subsurface. For ecologists, this matters because it means soils in sinkholes are often deep and moist, while the surrounding upland soils on cherty ridges can be thin, dry, and nutrient poor. Different soils, different water availability, different plants, and therefore different animals. Even within a short walk, you can move dramatically between different ecological worlds in the Ozarks. That contrast, dry rocky ridge versus moist sheltered hollow, is one of the signature ecological gradients of the Ozarks, and we'll return to it again and again throughout this course. Now let's talk about what the Ozark landscape actually looks like, the major habitat types that ecologists recognize, and what makes each one special. Because the Ozarks are not one thing. They're a mosaic of very different habitats, each shaped by geology, soils, topography, and history. The most extensive habitat in the Ozarks is the upland oak hickory forest. Drive almost anywhere in the region and you'll see it. Ridge tops and upper slopes covered in oaks, mostly white oak, black oak, and post oak in the drier uplands, mixed with several species of hickory. These forests were historically more open than they are today, maintained in a savanna-like state by frequent low-intensity fires, many of which were set deliberately by indigenous peoples for thousands of years to manage the landscape for hunting and travel. The suppression of fire over the past century has allowed these open woodlands to close in. The understory has filled with eastern red cedar and shade-tolerant shrubs, and many of the open-grown, widely spaced oaks that once defined the landscape have been crowded out. Ecological restoration in the Ozarks often involves prescribed fire to try to recover some of that openness. Cedar glades are one of the most visibly striking and ecologically unusual habitats in the Ozarks. A glade is an opening in the forest where exposed bedrock at or near the surface prevents trees from establishing. In the Ozarks, glades form on thin soils over limestone or dolomite outcrops, and they're dominated by eastern red cedar on the margins, hence the name. The interior of a glade is a harsh environment: exposed rock, shallow soil, full sun, temperature extremes. In summer, surface temperatures on bare rock in a glade can exceed 130 degrees Fahrenheit. In winter, there's no snowpack to insulate the ground. It's an environment that would seem to support very little life, but cedar glades are hotspots of botanical diversity. The plants that live there are specialists, uniquely adapted to those extreme conditions, and found nowhere else. Several plants, including the Ozark glade coneflower and the Missouri bladderpod, are found almost exclusively in Ozark cedar glades. They evolved here, in this very specific environment, and can't live anywhere else. That's a pattern you'll encounter repeatedly in Ozark ecology. Harsh, unusual conditions produce unique, specialized life. The places that look least hospitable are often the most interesting biologically. If glades are the hot and dry extremes, then forested hollows are the cool and moist extremes. Hollows are the north and east-facing slopes, ravines, and valley bottoms that receive less direct sunlight and collect more moisture. Here you'll find a completely different forest: sugar maple, American basswood, white ash, tulip poplar, and in the deepest hollows, enormous old sycamores along creek edges. These mesic forests, meaning moist, middle of the road in terms of water availability, are where spring wildflowers thrive. The combination of deep, rich soils, spring moisture, and a brief window of sunlight before the canopy closes above creates ideal conditions for the ephemeral wildflowers we'll explore in detail in Module 2. Hollows are also refugia, places where plants and animals can persist through disturbance or climate stress because the environment is locally moderated. During a drought, a north-facing hollow stays moister than the surrounding uplands. During a heat wave, hollow temperatures stay cooler. These microclimate refugia are critically important for biodiversity, and they're one reason the Ozarks have maintained such high species richness through climate fluctuations over thousands of years. Along the larger rivers and streams of the Ozarks, the Current, the Jack's Fork, the buffalo, the 11 point, you find floodplain forests, low, flat land that floods periodically and supports a different mix of trees and plants. Cottonwood, sycamore, silver maple, box elder, and various willows dominate these wet bottoms. Floodplain forests are critical wildlife corridors. Many species, deer, river otters, mink, wood ducks, and countless songbirds during migration move along river corridors as they travel through the landscape. The tradition zone between the river, the floodplain forest, and the upland slope, what ecologists call the riparian zone, is one of the most productive and diverse ecological interfaces in the entire Ozark landscape. And finally, scattered throughout the Ozarks are small but ecologically irreplaceable wetland habitats, fens and seeps. A fen is a groundwater-fed wetland. The water doesn't come from the surface rain, but seeps up from below, often emerging from a hillside where groundwater meets an impermeable layer of rock. Ozark fens are extraordinarily rich in plant diversity, including many rare and threatened species, grass of Parnassus, several native orchids, sundews, and carnivorous plants. They're also a breeding habitat for some of the region's most unusual salamanders. Most Ozark fens are small, sometimes just a few hundred square feet, but their ecological significance is outsized. They represent habitat types that once covered much larger areas, now reduced to fragments. Protecting a single fen may mean protecting the last population of a plant species in an entire county. I want to spend a few minutes on something that doesn't get nearly enough attention in popular ecology: soil. Soil is the interface between the geological world and the biological world. It's where rock becomes life, slowly, over thousands of years of weathering, decomposition, and biological activity. And in the Ozarks, soils are wildly variable because the underlying geology is wildly variable. On rocky ridge tops and thin-soiled glades, you have what soil scientists call ultisols or entisols, soils that are thin, acidic, and low in nutrients because the rock weathers slowly, and organic matter doesn't accumulate easily on these exposed, well-drained surfaces. Plants that grow here have to be tough, adapted to drought, capable of extracting nutrients from inhospitable substrates. In hollows and on north-facing slopes, you find deeper, richer, more moisture-retentive soils, often dark with organic matter from centuries of leaf fall and decomposition in a relatively sheltered environment. These are the soils where spring wildflowers flourish, where forest productivity is high, and where you find the most lush and diverse plant communities. And then there's a soil characteristic unique to cherty terrain, chert gravels. As limestone dissolves and weathers away over millennia, the insoluble chert nodules that were embedded in it are left behind on the surface. In many parts of the Ozarks, entire hillsides are armored in chert gravel, which creates a very specific soil condition: porous, well-drained, low in nutrients, and difficult for plants to root in. Yet, even here, specific communities of plants have adapted and flourished. When you're hiking in the Ozarks and you start noticing what's growing around you, try paying attention to what's under your feet. Is it bare rock, dirt gravel, deep dark soil, sandy creekside deposits? The soil will tell you exactly what plants to expect and often what animals you'll find as a result. Ecology is, in many ways, just applied geology. The rock, the soil, the water, they set the stage. Everything else, the plants, the animals, the entire web of life, performs on that stage. And to understand the performance, you have to know the stage. One more piece of context before we talk about spring, the recent biological history of the Ozarks. The Ozark Plateau wasn't glaciated during the ice ages. The glaciers stopped just to the north, but the region's climate fluctuated dramatically nonetheless. During glacial maxima, the Ozarks were much colder and drier than they are today, more like a boreal landscape with spruce and fir forests. As the climate warmed, those cold-adapted species retreated north and upslope, and warm-adapted species moved in from the south. But the Ozarks were never completely colonized and then wiped out like the glaciated regions. They served as a refugium, a place where species could persist through difficult periods because the topographic complexity of the landscape provided microclimates that buffered against extremes. North-facing hollows stayed cooler, south-facing glades stayed warmer. Springs maintained stable temperatures, and this means the Ozarks have been accumulating biodiversity for a very long time, adding species from multiple climate eras without losing the previous ones. It's like a library where books are only added, never removed. So you end up with an extraordinary collection. That long, complex history explains why the Ozarks punch so far above their size in terms of biodiversity. Missouri and Arkansas together host over 3,000 native plant species, hundreds of native fish species, more native fish diversity than almost anywhere in the temperate world, over 100 species of salamander, frog, and toad between the two states, and thousands of insect species. And every spring, this accumulated biodiversity wakes up all at once over the course of just a few weeks. Which brings us to the whole point of this course section on spring. Spring is the most ecologically eventful season in the temperate world. More happens per week in March, April, and May in the Ozarks than any other time of year, and here's why. Winter is a period of enforced patience. Cold temperatures limit enzyme activity in plants and animals. Daylight short, so photosynthesis is limited. Water's sometimes locked in ice. Energy is expensive to generate and easy to lose. And then, starting in late February or early March in the Ozarks, something shifts. Day length crosses a threshold. Soil temperatures begin to rise. Rain events become more frequent, and every organism in the ecosystem is tuned through millions of years of evolution to respond to exactly these signals. Spring ephemerals push up through leaf litter, racing to bloom and set seed before the canopy closes above them and steals their light. Frogs emerge from hibernation and migrate to breeding ponds on the first warm, rainy nights. Migrant songbirds pour through from their wintering grounds in Central and South America, following the food wave of emerging caterpillars northward. And those caterpillars are themselves responding to the precise moment that their host plants leaf out. Every species is on a schedule, and all those schedules interlock with each other in a network of timing and dependency that ecologists call phenology, the study of when things happen in nature and how those timings relate to each other. That's one of the most important frontiers in ecology today, especially as climate shifts the seasonal rhythms that organisms have relied on for millennia. Over the next 7 modules, we're going to be following this unfolding spring, week by week, from the first bloodroot blooms in March to the full canopy closure of late May. We're going to meet the plants, the animals, the fungi, the insects, and the water systems that make up the living Ozark. And my hope is that by the end, you'll never look at an Ozark hillside the same way again. You'll see the geology in the soil under your boots, the climate history and the species around you, and the ecological connections between a flowering trout lily, a mining bee, a wood thrush, and the cold spring branch running at the foot of the hollow. It's all connected. That's what ecology means. And the Ozarks are one of the best places in the world to see those connections. If you're watching this online and would like to take the Ozark Ecology course, you'll find it located inside the Ultimate Herbal Database under Courses.